Yes, sir.
Okay, okay, good. Is it visible to everybody now? So we have reached the fag end of this CFD course. So this is the new chapter we are starting. After that, there will be another chapter left. That is the special topics. So that will be finished the coming week. So I will be taking another two classes to finish the syllabus of the CFD. Okay, so let us start. In the last class, we have discussed the numerical methods that is generally used for the solution of Navier-Stokes equation. That means the stream function and vorticity approach, how one can employ the stream function and vorticity approach for the numerical solution of fluid flow problem that we have seen, and also we have solved one sample problem. That concludes the chapter on stream function and vorticity method. Now, today I will be discussing another very important numerical technique that is generally used for the numerical solution of convection and diffusion equations. So what we will be aiming into, to solve a convection diffusion equation and also the upwinding scheme. I think already we know what is convection and diffusion equations. Basically, Navier-Stokes equation is a basically convection and diffusion equation. So the equation contains transient term, convection term, and diffusion term. All those stuffs already we have discussed in the last class. Today we shall be discussing very important numerical techniques related to convection and diffusion equation. Is basically called the upwinding scheme. So what is upwinding scheme, that we shall see shortly. In general, for convection and diffusion kind of problem, so there are certain types of convections may present. One is called forced convection situation, when there is a continuous interaction between the fluid flow and heat transfer, but at the same time there is no change in density of the flowing fluid. That is called the forced convection situation. Another one is called the natural convection situation. There is no fluid flow, but there is a fluid flow due to the change in temperature gradient, and that causes change in density, which induces a fluid motion due to the thermal buoyancy. That is called the natural convection. Another kind of convection may present in practice or in reality. That is called the mixed convection. That is basically the combination of forced convection and natural convection together. That is called the mixed convection situation. So we have already studied what are those forced convection, mixed convection, and natural convection in the heat transfer courses. So here in the numerical methodology, what we will be primarily seeing that how one can apply the convection diffusion equation. One can apply the convection diffusion equation for the particular numerical solution of the problem through upwinding scheme. So what is the basically it's called the upwinding scheme. To understand why we require upwinding scheme for the numerical solution of any convection diffusion problem, here actually I have shown you a particular situation of one-dimensional steady convection diffusion problem. So basically, we'll be seeing that if we do not use upwinding scheme for the numerical solution of convection diffusion problem, we may face numerical instabilities. That means if we solve the convection diffusion problem numerically, the solution may not converge and the solution may be highly unstable. For example, let us see a typical example of convection diffusion problem is basically your vorticity transport equation. So let us go back to our earlier slides. So this is your vorticity transport equation. Let us go back. So this is your vorticity transport equation. Okay, this is the vorticity transport equation. This is a two-dimensional vorticity transport equation. Basically, there are two dimensions, x and y dimensions. This is basically two-dimensional vortex transport equation, where del zeta del t basically is your uh, temporal term, or call a time dependent term. And what is this term? U del zeta del x plus v del zeta del y. Shivnath, what
Inertial
is this
term.
term?
Convection term.
Yes, yes, it's the convection term. And this term is
Diffuse diffusive
uh,
diffusivity.
dif- not diffusivity. This is called the diffusion term.
Diffusion term, yes.
In any Navier-Stokes equation, there are, or any convection diffusion. Basically, this is a standard example of convection diffusion equation, where we have temporal term, basically time dependent term. This one is a convection term, basically convection, the movement of any property. Here properties is your vorticity, the movement of any property by fluid due to the fluid motion. Fluid motion along the u and v direction, that is along the x and y direction, causing movement of the property zeta along the particular direction. So movement of this property by the combined consequences of velocities called the motion of this particular property. That's why it is called the convection. Similarly, somebody wants to join. Okay. Similarly, here this is a diffusion term. There is no velocity term involved. So it's a pure diffusion case. So this is a diffusion term. This is a typical example of convection diffusion problem. Now, for this typical convection diffusion problem, if you want to solve it numerically, you may face numerical instabilities for a particular situation when your convection dominates over the diffusion. So if your convection speed is very high in compared to the diffusion, you may face numerical instabilities. To solve the numerical instabilities, basically in the appointing scheme generally used for the convection term only. So that I will be discussing soon. So let us go back to our discussion, convection diffusion problem. So let us consider one-dimensional steady convection diffusion problem. One-dimensional steady convection diffusion problem. Let us consider a particular slack type of flow. Slack flow means where velocity is very small and velocity is uniform. So there is no variation of velocity along the y direction. This is your x direction, and this is your y direction. There is no variation of velocity along the y direction. This is called the slack flow. Very low Reynolds number flow, slack flow, something like creeping flow time. Creeping flow is much lower than the slack flow. So, for example, flow of liquid steel, flow of metal, liquid metal, those kind of flow situation is called the slack flow. So why we have chosen this problem? Because this kind of flow analytical solutions are available. So basically, from the analytical solution, we would like to show you, if you don't use your appointing scheme or particular numerical scheme, you may not able to get converges in the solution, or sometimes you may get absurd or unrealistic physical solution. So to understand the situation, I have chosen this problem of slack flow for one-dimensional steady convection diffusion problem. So let us consider a slack flow, that is a flow with a uniform velocity. Velocity is very small and uniform. There is no variation of velocity along the y direction, and unidirectional, that is only x direction velocity exists. Y direction there is also existence of velocity, but those are uniform. There is no velocity variation. So fluid is entering into this domain, or fluid is going inside the domain with an uniform velocity u naught, and it is also exiting from the domain with the same uniform velocity u naught. But at the same time, there is a variation in temperature. So at the inlet of the domain, so this is the domain, at the inlet of the domain, your velocity is, temperature is T naught. At the exit, your temperature is T1, where T1 is greater than T naught. Basically, your inlet temperature, outlet temperature is more than the inlet temperature. But your velocity is same, inlet and outlet velocities are same. At the same time, throughout the whole domain, velocity is also same. Velocity is uniform. So this kind of situation is basically called the slack flow situation. So here I have shown you the typical boundary condition. So at the inlet, which is basically you can call x less than or equal to 0, because x axis is starting from, so basically origin is starting from this point. So once you moving along this direction, so basically x will increase. That means Along this direction x will increase, but from along this direction x will decrease. Basically x will be negative. So along this direction we have a temperature is T naught, velocity is u naught. But if this is the length of the domain, if this is the L is the, suppose L is the length of the domain, here I have not shown here. So if suppose L is the length of the domain, so at the exit your temperature is T1. So at the exit there is a temperature which is T1. So at x greater than or equal to L, so x equal to L or x greater than L, your temperature is T1. So that means there is a variation of temperature inside the domain, right? There is a variation of the temperature inside the domain. We would like to see how the temperature is varying inside the domain for this typical one-dimensional convection diffusion problem. That means we want to evaluate the temperature distribution Tx. Basically here T will be function of x only because the flow is uniform, unidirectional, steady, velocity is also uniform. So T will be function of x only x. So how the temperature is varying along the length of the domain, which is L, and which is function of x, basically that we shall determine from both analytical and numerical considerations. Is there any difficulties in understanding in this slide? Is that clear to all of you? Any question?
Sir, then what
Yes.
influences the fluid in increasing the temperature?
Yes. Yeah. So no. Actually, what we have done, we have fixed the boundary condition such that your outlet temperature is T1. Basically, what is happening inside the domain, there is an interaction between the fluid flow and temperature. But suppose you may consider a situation, you have a domain at inlet, you are fixing a temperature say 30 degree. At outlet of the domain, you are adding some heater and you are maintaining the temperature at say 50 degree. And inside the domain there is a fluid flow. So what will happen? There will be interaction of the temperature because this situation will cause an enhancement in temperature from the inlet to outlet due to the motion of the fluid. The motion of the fluid is causing the enhancement of the temperature from the inlet to the outlet. Understood? Or no?
Yes, sir. Yes, sir.
Is that clear to everybody? Or any other questions you may have? Clear?
Yes, sir.
Okay. So that means basically we have chosen a model problem. So let us, this is a model problem where your inlet temperature is T naught, outlet temperature is T1, which is T1 is greater than T naught, and fluid is flowing with an uniform velocity, which is U naught, and it is throughout the, basically velocity is same throughout the whole domain, and fluid is flowing at a uniform velocity. Now, if we want to write the corresponding governing equation for this problem, what will be the governing equation for this problem? Can anybody tell me? What is the governing equation for this problem? Yes? What is the governing equation for this problem?
লেখা আছে তো u0 dt dx equal to alpha.
No, how it
d2
is
dx.
coming? How it is coming? My question is how it
The
is
flow
coming.
is only in the x direction. Then from the energy equation, we
Very
will
good.
get after
Yeah.
neglecting all the term.
Yes. True. That is the answer. Basically, flow is governing only in the x direction, and the governing equation is basically your two-dimensional energy equation. So if you apply the energy equation, so what will happen? Your unsteady term will go away because there is no unsteady term. U naught will be constant because velocity will be constant. There will be only one temperature gradient will be existing only at x direction, but y direction v is zero. Velocity, there is no velocity along the y direction, so v will be zero, and then alpha del 2 t del x2 plus del 2 t del y2. So del 2 by del y2 will not be there because there is no temperature gradient along the y direction. Del t del y is zero for the temperature gradient in the y direction. So finally we will be getting this simple one-dimensional governing equation for which governs the temperature distribution along with the flow inside the domain. This is the energy equation of the problem under consideration. That is u naught dt dx equal to alpha d2t by dx2, where u alpha is your thermal diffusivity, right? This is your governing equation. Now what we have to do, again we have to make the governing equation dimensionless. So let us introduce likewise. We did it earlier, that we have introduced a non-dimensional scale theta is a dimensionless temperature. Basically, T minus T naught divided by T1 minus T naught, where T1 is the outlet temperature, T naught is the inlet temperature. So we are making the temperature dimensionless with respect to T minus T naught by T1 minus T naught. X equal to small x by L. Similar thing. X equal to small x by L. Now we are defining a dimensionless number. So if you introduce the dimensionless parameters into the governing equation, so you will be there will be another, you will see there will be another term, another dimensionless parameter will be coming, that is u naught L by alpha. U naught L by alpha. Basically that is called the Piclet number. Piclet number or Piclet number, whatever you call. This is the Piclet number. So this is the typical dimensionless number. Likewise, we have a Reynolds number, we have a Prandtl number, we have a Smith number for chemical engineering, so Nusselt number for heat transfer. Similarly, there is another number which is called Piclet number, which is defined as U naught L by alpha. So what is the physical significance of Piclet number? Piclet number, you can say, you can see is a ratio of some velocity into L divided by alpha. So basically, this is the velocity term is present in the numerator. That is, we call it due to the fluid motion. The fluid motion term is present here, and this is the diffusion term. Alpha is your thermal diffusivity. So Piclet number basically signifies the relative importance of convection to the diffusion. Relative importance of convection, because U naught L, relative importance of convection to the diffusion. So if Piclet number is very high, your convection will be very high compared to the diffusion. If Piclet number is very less, your diffusion will be very high in compared to the convection. Is that clear? Is that clear? This will be required for numerical solution.
Yes, sir.
Okay. So that is the Piclet number that we have seen, that we have obtained a Piclet number after making the governing equation dimensionless. So finally we will be getting Piclet number d theta dx equal to d2 theta by dx2. This is your governing dimensionless form of governing equation. So if you make your governing equation dimensionless after incorporating these dimensionless variables, you will be getting this. You will be getting this dimensionless form of governing equation. So okay, so what are the boundary conditions again? So here we can see, I think one thing is coming to be okay. Okay, so this is the dimensionless form of equation. Dimensionless form of equation P d theta dx, P d theta dx equal to d2 theta by dx2. This is the dimensional form of equation. So what are the boundary condition? At x equal to 0, that is the inlet of the domain. At x equal to 0, at t equal to t naught. That means if you put t equal to t naught here, theta will be 0. And at x equal to 1, x equal to 1 means that x equal to small x equal to capital L. That is the outlet of the domain. X equal to capital L, x equal to capital L. Your capital X equal to 1. If you put small x by capital L, your capital X will be 1. And theta is t naught, theta is t1, theta is t1. That means if you put t1 here, theta will be 1. This is the boundary condition. Boundary condition 1, at x equal to capital X equal to 0, theta equal to 0. And at capital X equal to 1, theta equal to 1. These are the two boundary conditions at the inlet and outlet of the domain. And this is your dimensional form of governing equation. Now this equation can be solved analytically. Very simple. If you use this dimensionless boundary condition along with the dimensionless governing equation, you may solve this equation analytically to obtain an analytical solution of temperature distribution, that is theta x equal to exponential Piclet number into x minus 1 by exponential Piclet number minus 1. This is the analytical solution. That means if you want to solve, if you can solve this problem, this differential equation can be solved analytically. By analytical means to obtain a temperature distribution, analytical temperature distribution as theta capital X equal to exponential Piclet number x minus 1 divided by exponential Piclet number minus 1. This is the analytical temperature distribution. Let us examine this analytical solution for different Pictet number values. Let us consider when Pictet number is closer to 0. Pictet number is very less than 1. It is closer to 0. So what will happen? Theta x equal to capital X, right? Is that right? When Pictet number is closer to 0, what will happen? Pictet number tending to 0. Theta x equal to capital X. Is that okay?
Yes, sir. Yes, sir.
How you are getting this theta x capital X?
Sir, limit
Yes, good.
Pictet
Okay.
number tends to 0, and then this term. Then
Okay.
e to the power px minus 1 by 2 by p minus 1.
Yes, true. So you are obtaining theta x equal to capital X. That is, temperature is increasing with length. That is a pure conduction situation. There is no convection present because Pictet number is 0, nearer to 0. No convection term is there. So temperature is linearly increasing with distance. This is the situation that you may obtain, or this is the inference that you have obtained from the analytical solution. Theta x equal to capital X. That means temperature is linearly increasing from the inlet to outlet. Theta x is capital X. If x increases from the inlet to outlet, theta x will be linearly increasing from inlet to outlet. Right? Now, when Pictet number is very greater than 1, Pictet number is very greater than 1, what will happen? Your convection will be dominating, your diffusion will be less, the flow will be a highly convective flow, convection will be highly dominated over the diffusion. So it will be a highly convection dominated flow. U naught L will be very greater than alpha. So it will be primarily convection dominated flow. So in that situation, what will happen if the convection is dominating over the diffusion for Pictet number very greater than 1? That means your temperature gradient would be very much limited to x equal to 1. That means your temperature gradient dt dx for a situation when Pictet number is very greater than 1, it will be limited to its region nearer to the exit of the domain, because whatever flow is coming, it is forcing the temperature nearer to the forcing the temperature to decrease from the inlet, and it will increase nearer to the wall, nearer to the outlet. So that means temperature gradient will be confined nearer to the outlet of the domain. So how it is coming? That means temperature gradient theta equal to 0 to 1 it will be confined near to the x equal to 1. So let us see. So temperature gradient at x equal to 1 d theta dx. Let us examine this consideration. D theta dx at x equal to 1, which is what is that? P expression px by expression p minus 1, right? X at x equal to 1. So that x equal to 1, if you put x equal to 1, that is p expression p by expression p minus 1. So for p Pictet number very greater than 1, so this will be equal to p. That means you can write expression p minus 1 as expression p, and expression p expression will be cancels out, and it will be finally it will yield as equal to p for expression very greater than 1. That means temperature gradient for Pictet number very greater than 1, it will be limited to a region near to the wall. So let us plot these three situations. That is what is the variation of temperature with distance from the inlet to outlet, how the dimensionless temperature is varying from the inlet to outlet. That for P equal to 0, that is purely conduction case, there is no convection present, P equal number equal to 0, that is no convection present, pure conduction. No convection present, that is no convection present, pure conduction. d2 theta dx2 equal to 0, pure conduction equation. That means your temperature will linearly increasing from inlet to the outlet, linear variation, Pictet number equal to 0. Pictet number greater than 0, there will be some variation. It will be something like, it will show some, some kind of this kind of exponential variation. This kind of exponential variation. Pictet number greater than equal to greater than 0. When Pictet number very greater than 0, that we have seen from this analytical calculations, that your temperature gradient dTdx will be very steep. It will have very steep temperature gradient, and temperature gradient will be limited closer to the outlet of the domain, at closer to x equal to 1. So you can see at the inlet, near to the inlet region, so at, say for example, if it's a mid plane, near to the mid plane, there is certain change in temperature gradient, and it will reach its maximum value at x equal to 1. So before that, it will be very less. This is called steep temperature gradient. So before x say capital X equal to 0.5, there is hardly any variation in temperature. Theta x is closer to 0. But beyond x equal to 0.5, it will be suddenly changing to a value theta equal to 1, closer to x equal to 1. So this is called the steep temperature gradient. Any doubt on this plot? Because this is very important plot. Any doubt up to this? Any doubt? You may ask if you have any doubt. Yes? Any doubt? Anybody has any doubt?
No, sir.
Understood everything?
Yes, sir.
Okay. So you can easily, this is very simple consideration, that nearer to x equal to 1, there is a steep temperature gradient. You can see the variation if we plot theta x versus x, that is, I am plotting this expression, theta x versus x, how theta x is varying with the x, theta x versus x. If you plot for peak number equal to 0, you will have a linear variation that already we have seen, theta x equal to x, if you put peak number equal to 0. And if you greater than 1, there is exponential variation. And for very greater than 1, it will be changing from x equal to 0.5. There is steep temperature gradient near to x equal to 1. You can see steep temperature. Basically, this is a function of Pickley number. This is the analytical solution, and this is a plot of analytical solution. Let us solve this problem numerically with finite difference method, and let us compare the analytical and numerical solution together and see what is the consequences of the numerical solution. Let us solve this numerical solution numerically. So what you have to do? You have to discretize the domain in number of grid points. So let us start from I equal to 1, I equal to, so up 0, 1, 2, 3, up to I equal to -1. Say I equal to I here, and I equal to I plus 1, and I equal to n plus 1. This is the situation. And let us say distance between the two grid points is delta x, so on and so forth. Now, if you discretize this equation under finite difference method, due to central differencing, what will be the equation? That is, this is the equation. We are discretizing this equation. So what we are doing here, we have solved this equation first analytically. Now we are solving the same equation numerically and see what is happening for Pickley number very greater than 1. What is happening for different Pickley number values for the numerical solution. So Pickley number, this is the equation. We are now discretizing the equation. Pickley number theta I plus 1 minus theta I minus 1 by 2 delta x. Already you know this. Equal to theta I plus 1 minus 2 theta I plus theta I minus 1 by delta x square. This is the discretized form of this governing equation. Now, let us define another Pickley number, which is called cell or grid Pickley number. So both are same basically. So this cell Pickley number, grid Pickley number, basically why we are calling the cell or grid Pickley number. Basically, we are multiplying the original Pickley number with delta x. That's why we are calling it cell Pickley number, PEC. This is nothing but PE, but with a scaling parameter delta x. This is we are calling it cell Pickley number, PEC. So now, if we use this definition of cell Pickley number, PEC, which is equal to Pickley number into delta x, and if you do some algebraic manipulations on this discretized equation, you will be getting this as PEC into theta I, PEC by 2 theta I plus 1 minus theta I minus 1 equal to theta I plus 1 minus 2 theta I plus theta I minus 1. That means theta I equal to 1 by 4, 2 plus PEC theta I minus 1 plus 2 minus PEC theta I minus 1. These are the two things you are getting. So after writing this equation, or after doing some mathematical or algebraic manipulations, you are writing theta I as 1 by 4, 2 plus PEC theta I minus 1 plus 2 minus PEC theta I minus 1. So I think there is a mistake here. It should be theta I plus 1. This should be theta I plus 1. I don't know how this mistake is coming here. This is theta I plus 1, and This will be theta I plus 1. Okay. So what you are doing is simply writing this equation as theta I equal to 1 by 4 2 plus PEC theta I minus 1 plus 2 minus PEC theta I plus 1. Basically, you are simply writing this equation theta I is a function of theta I minus 1 and theta I plus 1. Let us see what is happening. Zero. Pick number is tending to 0. What is happening? Theta I equal to half of theta I minus 1 plus theta I plus 1, right? Half of theta I plus 1 I minus 1 plus theta I plus 1. My pick number is 0, let us say. That means temperature is basically pure conduction temperature. So temperature, what it is showing here, basically it is under the conduction regime. Why it is under the conduction regime? Can anybody answer this question? Why I am calling this pure conduction?
The convection term is equal to 0. That is why the Peckley number is 0.
Yes. So that is a pure conduction region. That means the analytical, there is a numerical solution also. If you solve this problem numerically for Peckley number closer to 0, we are getting a numerical solution which is basically corroborating or which is basically satisfying the analytical solution that already we have obtained. Analytical solution. Temperature basically analytical solution. Theta x equal to x is a pure conduction region, Peckley number tending to 0. Here also, theta Peckley number tending to 0, we are getting theta I equal to half of theta I minus 1 plus theta I plus 1. That is, temperature is increasing with the x because we are increasing delta x by, we are increasing along the length of the domain. Temperature is increasing along the length of the domain. So theta I basically half of theta I minus 1 plus theta I plus 1. There is no problem if we, when the Peckley number is very low, the Peckley number is closer to 0. For the convection diffusion problem, there is no issue when Peckley number is closer to 0. That is, Peckley number is tending to 0. We are getting a numerical solution which satisfies the analytical solution, because analytically also we are getting theta x equal to x. That means temperature is increasing with the distance from the inlet of the domain, theta x equal to x. Here also in numerical calculations also we are getting the similar expression theta I equal to half of theta I minus 1 plus theta I plus 1. That is, temperature is increasing from the inlet of the domain. So similar, exactly similar solution that we have obtained for the analytical calculation. This analytical calculations and numerical solutions are matching with each other. That is, we are getting similar solution. So there is no issue when Peckley number is tending towards 0. That is the situation when Peckley number is closer to 0. Now, what is happening when Peckley number is very, very greater than 1? That is very high Peckley number flow. When the Peckley number is very, very high, Peckley number is very, very greater than 1. If Peckley number is very, very greater than 1, what will happen? Theta I equal to 1 by 4. So this one is 2 plus Peckley number C equal to basically Peckley number. If Peckley number is very, very greater than 1. So we can write this equation number 1 as theta I equal to 1 by 4 Peckley number C you can take common. Peckley number C theta I minus 1 minus theta I plus 1. 1 by 4 Peckley number C theta I minus 1 and theta I plus 1. So now tell me what is wrong in this solution. Why we are calling this solution is not okay? What is wrong in the solution? Can anybody answer this question?
The second solution, I think the value will be negative. No.
Yes.
Sorry. For Peckley number very, very great, the convection is more dominant. The value of theta, theta I will be negative, I think, because theta I minus.
Yes. It will be negative, right? So then, if it is negative, what is wrong? If it is negative, what is wrong? Would the temperature will be negative? Is that possible physically? Yes.
No, sir.
So if the Peckley number is very, very greater than 1, what will happen? See, you can see, as correctly pointed out by Deep, you are absolutely right. Your Pickley number is very, very greater than 1. What will happen? Theta I plus 1 is more, because the next grid point, this is the next grid point value, it is the previous grid point value, so it will be theta I will be negative. But in reality, negative temperature is not possible, right? Temperature will be negative, because the domain here temperature is increasing from the inlet to outlet. So that means in between you are getting negative temperature. Is that possible? Physically, is that
No,
possible?
sir. No, sir.
It is not possible. It is not possible. That means if you solve this problem numerically for very high Pickley number flow, you may get a solution which is physically absurd or physically not possible. And also at the same time, if you see this equation number 1, if you recall the von Neumann stability analysis that we did it for the convection diffusion problem, that for Pickley number greater than 2, the solution is unstable, because here 2 minus Pickley number is coming. So this has to be greater than 0. That means Pickley number is less than 2, then only the solution is stable. For greater than 2, the solution is not unstable. That means we are getting some negative solution. So that is physically not possible, and physically it is yielding an absurd solution. That means as a result, we may get a Eagles or oscillation in the computer in the computational technique. So you may get in the oscillation in the numerical solution, which is called Eagles, which is termed as Wiggles. Wiggles means you are getting an oscillation in the numerical solution. Solution will not converge, and also you will be getting a solution which is physically not possible. That is, you will be getting one negative temperature inside the domain, which is physically not possible. So this is the problem. That's why one needs to apply an upwinding scheme in the convection term while solving a convection diffusion problem numerically. Have you understood why we want to use upwinding scheme, but what is the problem of convection diffusion equation if you want to solve it numerically? Have you understood now?
Could you please repeat it again? I cannot understand.
Sorry, I'm not able to hear you properly.
Could you repeat it again?
Okay.
Wiggle
So,
term.
Wiggles means actually, you can see for Pickley number very, very greater than 1, what is happening? You are getting a negative temperature, right? Negative temperature,
Yes,
you
sir.
are getting. Temperature negative is not possible here in this domain. If you get negative temperature, what will happen? Your solution will be diverging. You'll be getting a solution of temperature which is negative, and that is a physically not possible, physically absurd solution, right? That is called, if some physically absurd solution you will be getting, if when you start getting the physically absurd solution, you will be seeing that there is some oscillation in the convergence of the numerical solution. If you find the error in the while solving the problem numerically, you will see that error with time will be oscillating. That oscillation in the error or oscillation in the convergence is called the Wiggles. Understood? Wiggles, what is called the Wiggles? Let us explain it here. That means, suppose you are solving the problem numerically, this is the error, epsilon with time. Now you will see oscillation in the error. This kind of oscillation. This is called Wiggles. Or Pickley number is very, very greater than 1. Now understood?
Yes, sir.
Ideally, you would have get this kind of convergence, but you are not getting. You are getting this kind of convergence. That is, you are not getting convergence at all for a high Pickley number flow. You are getting very high oscillation in the numerical solution, which is basically a manifestation of numerical instability, and that is called the Wiggles in the numerical solution. Now you have understood?
Yes, sir.
To prevent this oscillation in the numerical solution of the governing equation while solving convection diffusion problem, one has to apply upwinding scheme, or we call upwinding method, in the convection term of the governing equation. So it is the convection term. This is the convection term. In the convection term, while discretizing the convection term, you should apply the upwinding method for the convection term only, not in a diffusion term. Upwinding method you have to apply in the convection term only. This is the while discretizing the convection term, you should apply the upwinding scheme, not in the diffusion term. So that means if we apply upwinding scheme in the convection term, this wiggles or numerical instability or computational instability can be avoided or could be avoided. So what is the upwinding scheme? Let us discuss what is. This is a very important scheme, and this is one of the very important method. If you find any commercial software or if you write your own code, that everywhere you will see what type of upwinding scheme you have to choose, or type of upwinding scheme you have to choose for the solution for the numerical solution of convection diffusion problem. Because all the problems in reality, whether it is Navier-Stokes equation or Navier-Stokes or energy equation, all the problems are basically of convection diffusion type. And for this convection diffusion type of problem, you must apply a upwinding scheme to avoid the numerical instabilities or the computational instability, that is the problem that is manifested as a wiggles in the numerical solution. So that means this is the governing equation. You are discretizing the governing equation in a finite difference method. Piclet number theta I plus 1 minus theta I minus 1 over 2 delta x, and theta I plus 1 minus 2 theta I but theta I minus 1 delta x square. This is the discretization form of equation. Now you have to apply the upwinding scheme on the convection term. That is here, in this term, while discretizing this term, you have to apply the upwinding scheme. So what is the upwinding scheme that I have written here? If u0 greater than 0, that means if the velocity is in this direction, theta I plus 1 must be replaced by theta I. If u0 is greater than 0, that means u0 is in the positive x direction, velocity is in the positive direction, theta I plus 1, value of temperature, non-dimensional temperature at the grid point theta I plus 1 has to be taken from the off station temperature value, off station grid point, that is theta I. And if u0 less than 0, if the velocity is along this direction, theta I plus 1 has to be taken from the off station grid point, that is theta I plus 2. Understood? Is that clear? This has to be very much clear, because in examination I will ask the upwinding scheme. Is that clear?
Sir, could you explain it once again?
Okay. Suppose this is a computational grid point. Suppose this is your I grid point. This is I plus 1. And this is, say, suppose this is I plus 2.
Yes, sir, it's audible.
Okay. Just a minute. Okay. So these are the grid points. Say, now suppose your velocity here it is u0 is greater than 0. That means fluid is flowing along this direction, along the positive x direction, let us say. In the convection term, what is there? In the if see this is a convection term, theta I plus 1 minus theta I minus 1 by 2 delta x. That means your convection term, you are discretizing the convection term as del theta del x as theta I plus 1 minus theta I minus 1 by 2 delta x. Okay. Now at any grid point, say let us say you are now obtaining this temperature gradient at grid point I for the convection term, because I am talking about the convection term only, this term. So at any grid point, you have to check whether u0, if u0 is greater than 0, if the fluid is flowing along the positive x direction, you have to replace theta I plus 1, that is theta I plus 1, you have to take from the upstation's value, that is a theta I, that is theta I plus 1, you have to replace by theta I. That means this expression you have to write as theta I minus theta I minus 1 by 2 delta x. Okay, understood? This is called the upwinding scheme. That means this value has to be taken from the previous station value, that is theta I. Temperature at theta I plus 1 grid point has to be chosen or has to be taken from its upstation value, that is theta I value. That is upstation. Which one is upstation? Theta I is the upstation. So this value you have to choose. That is value you have to replace in place of theta I plus 1. That means in place of theta I plus 1, you have to write theta I. Similarly, if the velocity is along this direction, if u0 is less than 0, velocity is along this direction. So that means in that case, your theta I plus 1 have to be taken from its upstation value. Upstation is theta I plus 2. That means theta I you have to replace as theta I plus 2 minus theta I minus 1 by 2 delta x. Is that clear now? This is very important. Is that clear?
Yes, sir, it's clear.
Okay, so it is very easy. I think. So if you want to, you have to just upstation value. You have to apply the upstation temperature value. That means when u0 is greater than 0, that is the velocity is along this direction, you have to replace theta I plus 1 by its upstation value, right? Theta I plus 1 by its upstation value theta I. When u0 is along this direction, you have to replace theta I plus 1 by its upstation value, which is theta I plus 2. So that is called the upwinding scheme. Perhaps it is called, basically, not perhaps, it is called the first order upwinding scheme. This is called the first order upwinding. So this kind of upwinding scheme is called the first order upwinding scheme. That is replacing the grid point value by its upstation value. Please remember, upwinding scheme is only applicable for the convection term only. That is, for the convection term only, you have to apply this upwinding scheme, not for the diffusion term. It is only meant for the convection term only. So for the convection term, there is this term. While discretizing this term, you have to apply this upwinding scheme. Now let us say we are applying this. This is called first order upwinding scheme. Now, if you replace theta I plus 1 by theta I in this discretized equation, so what will happen for theta I minus 1 by 2 delta x? So this will be same. Here we are not replacing anything. So theta I plus 1 minus 2 theta I by theta I minus 1 delta x square. That means theta I equal to 1 plus PEC theta I minus 1 plus theta I plus 1 by 2 plus PEC. So let us see if PEC is closer to 0, theta I equal to theta I minus 1 by theta I plus 1 by 2 is the exact solution you are getting. The same solution you have got theta I minus 1, theta I plus 1 by theta I without appointing. That means for the lower Piclet number, you may not apply appointing scheme. That is, appointing scheme is giving the exact solution. Now for higher Piclet number, the Piclet number is very greater than 1, greater than 1. So what will happen? If it is very greater than 1, that means theta I equal to theta I minus 1. This term will not be there. So Piclet number into C, Piclet number is very greater than 1. This term can be neglected. This term also can be neglected. It will be PEC into theta I minus 1. It will be only PEC. PEC will be cancelled out, and it will be theta I equal to theta I minus 1. That is the exact solution, right? That means your upstream temperature is basically governed by the downstream temperature. Upstream temperature is basically governed by the downstream temperature. So that is we are getting from the appointing scheme. So that means with the appointing scheme, the problem of getting the absurd solution, or problem of getting non-realistic unphysical solution can be circumvented by applying this appointing scheme. Have you understood this? Is there any issue in understanding?
Sir, for the Piclet number more than 1, how the theta I plus 1 is neglected here?
Okay. So দেবাশিসদা একটু ক্লাসে আছি, হ্যাঁ পরে ফোন করছি। হ্যালো।
Yes, sir.
Hello. Okay. The question is that how theta plus 1 can be neglected for Piclet number very greater than 1, right? That was the question, Simnath?
Yes, sir.
Okay. Now, if Piclet number is very greater than 1, that means 1 plus Piclet number is basically Piclet number, right? Right?
Yes, sir.
Okay. Let me write it here. I think you have some difficulties in understanding. What we are getting? 1 plus Piclet number into theta I minus 1 plus theta I plus 1 divided by 2 plus Piclet number, right? Right? This is the expression. Okay.
Yes, sir.
Now, if Piclet number is very greater than 1, there is a very high Piclet number. So what will happen? 2 Piclet number can be written as Piclet number. Right?
Yes, sir.
Very high. So that means 1 lakh plus 2. So we can neglect 2. That will be 1 lakh only. Clear? That is, suppose
Yes, sir,
10 to the power 5 plus 2. What is that? You can write as 10 to the power 5 only. There is no point of writing 2. 2 is very less compared to 10 to the power 5. Yes. So this is 2 plus Piclet number is Piclet number. Similarly, 1 plus PEC into theta I minus 1. This is equal to PEC into theta I minus 1.
Okay, sir, understood.
Okay.
Compared to PEC into theta
I plus
minus
1?
Yes, the theta I plus 1 term is very small.
Very small.
Yes, sir.
Yes. Now this one will cancel out. So theta I will be
Okay, sir. Okay,
theta I
sir.
minus 1. That means the exact solution you are getting from this appointing scheme. Please understand this scheme very well, because this is one of the important scheme in CFD technique. Throughout your CFD understanding, this scheme will be very much essential. Okay. Once you have understood this scheme, you can apply this scheme for numerical solution of any convection division problem, because all the problems are primarily in CFD are convection division problems. So there you will be needing this scheme. Okay, that means for a very high Piclet number, we are getting a solution which is closer to the exact solution. That means the problem of getting the absurd solution that we are getting when there is no appointing scheme is circumvented. Right?
So one question.
Yes.
Sir, for particular number very greater than one, most of the temperature distribution is like an exponential. It is mostly contained in the x equal to one region.
Yes.
So, but how can this solution theta I is equal to theta I minus one give that exponential distribution like it was shown? Because if
Okay.
suppose
Okay.
theta I minus one is 0.5, that then theta I is equal to always 0.5 is like it's converging like that.
Okay. 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 That means theta I equal to theta I minus one, right? Theta I equal to theta I minus one, right?
Yes, sir. Yes, sir.
Now that is theta one equal to theta at one equal to closer to theta at a previous station value, right?
Yes, sir.
Now, but here theta equal to one, here theta equal to zero, here it cannot be theta one, right?
No, sir.
So it will be slowly, it will be increasing to one. It will be slowly increasing to one, right? But how it is slowly increasing to one? It is slowly increasing to one from this point. But it will be one here, it will be one here, one here, one here, then one, then it will be lesser, then it will be minimized. Beyond that, it will not proceed because peak number is very greater than one. Beyond that, it will not proceed. Analytically, you are getting beyond that point, it will not proceeding to a value which is comparable to theta equal to 0.5 or closer to 1. That's why we are getting a numerical solution which shows that theta I equal to theta I minus 1. That means for very high peak number value, we are limiting to a situation, or we are getting a solution which is closer to 1 near to the location at x equal to 1. Is that clear or no? Tell me clearly. Huh? No, right?
No, sir.
Okay. 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 So this is your domain. This is theta 1. So this will be always theta 1, right? Theta equal to 1, it will be always.
Yes, sir.
And theta equal to 0, it will be always. Right?
Yes, sir.
So here, theta 1 equal to theta 2, right? That means here theta
Yes.
equal to 0. Here theta equal to 0. Here theta equal to 0. Here theta equal to 0. But here theta equal to 1.
Yes, sir.
Theta equal to 1. 1, 1, 1. But there is a 0. There should be a transition region, right?
Yes, sir.
So how the transition region happening? A small gradient. It will be 0, 0, 0, 0, then a small gradient nearer to the 1. Clear now?
Yes, sir.
Is that clear? So from this
Yes, sir.
direction, so if this is the line, from direction 0 value is coming. 0, 0, 0. This direction 1 value is coming. 1, 1, 1, 1. It cannot be suddenly 0 to 1 from here. It cannot be, suppose here we are getting another 0, but it cannot be 1 here. 0 equal to 1 not possible, right? So there will be sudden transition to 1. That is manifested by theta I equal to theta I minus 1. Is that clear now?
Yes, sir.
Yes, sir.
Okay, so I think this is very simple. You just think of it. If you don't understand again, you just give a thought experiment. Then you will get to know why I'm saying that this is an exact solution. Okay, so this is basically your upwinding scheme, and that upwinding scheme I have discussed in this class. Basically, this is called the first order upwinding scheme. There are other upwinding scheme. So equation 3 basically is a computationally stable. Here I could say 2 plus Pictet number is coming, 1 plus Pictet number is coming. There is no term is called 1 minus Pictet number or 2 minus Pictet number that we got while discretizing without applying the upwinding scheme. Here 2 minus Pictet number is coming, but here simply 2 plus Pictet number plus term is coming. So there it is always stable, like your implicit scheme, always stable. Upwinding scheme is always stable. Basically computationally stable. There are other versions of upwinding scheme. Basically, this upwinding scheme has called the first order accuracy. That's why it is called the first order upwinding scheme. There are other upwinding scheme also possible. It is called second order upwinding scheme. that I will not discuss because it is not in the scope of your syllabus. It's called second order Apoorni scheme. Basically, there instead of taking one upstation point, two upstation point are taken, 1 and 2, I and I minus 1. Theta I has to be replaced, theta I plus 1 has to be replaced by a function of I and I minus 1. It's called second order Apoorni scheme. Another Apoorni scheme is called third order Apoorni scheme or quick scheme. Sometimes it is called quick or other scheme is called third order. This Apoorni scheme has called third order accuracy. So depending upon the order of accuracy, Apoorni schemes are basically classified. Second order Apoorni scheme has got second order accuracy. That means instead of theta I equal to theta I plus 1, theta I plus 1 by theta I plus 1 has to be expressed some function of theta I and theta I minus 1. There is two observation values are taken. It's called second order Apoorni scheme. And third order Apoorni scheme, instead of one station value I plus 1 has to be replaced as a function of I minus 1, I minus 2. It's called third order Apoorni scheme or quick scheme. Okay, so in ANSYS plan you will be seeing this. What is second order Apoorni scheme, third order Apoorni scheme, or quick scheme? Those are actually there. Okay, this is the first order Apoorni scheme, and this is under the scope of your syllabus. That's why I have discussed first order. So and second order Apoorni scheme and third order Apoorni scheme, nothing but thus taking instead of taking one station up value, you have to take two stations, I and I minus 1. Third order, you have to take I minus 1 and I minus 2. Understood? Is that clear?
Yes, sir.
Okay. So second order and quick I have discussed. There are these two schemes. There are, although this Apoorni scheme is basically these schemes is not basically there are certain limitations. Means this scheme also introduces a diffusion, or sometimes it is called false diffusion in the numerical solution. So that is called the limitation of Apoorni scheme. So Apoorni scheme sometimes introduces diffusion, additional diffusion in the numerical solution. So that is called the false diffusion. So it is a primary limitation of Apoorni scheme. Although the Apoorni scheme is very computationally stable, it provides stable solution, but it introduces an additional diffusion or extra diffusion in the numerical solution of the convection diffusion problem. That is called false diffusion. What is a false diffusion? That for a very high Piclet number flow, what is happening? Very high Piclet number flow, del theta del x is nearly 0 at x equal to 0.5, right? That you can see. Please understand this concept. What is false diffusion? How it is Apoorni scheme introduces an additional diffusion to the numerical solution. See, at very high Piclet number greater than 1, this is a solution, analytical solution, also numerical solution, theta x versus x, right? What is happening when Piclet number is very large? Del theta del x is nearly 0 at x equal to 0.5. That is at discrete point, right? Is that true?
Yes, sir.
Now what is happening? If you calculate del theta del x, that means del theta del x nearly 0 at theta equal to n minus 1. That means, let us explain what is false diffusion. So if you want to calculate del theta del x at a midpoint, at theta equal to n minus 1, what is happening? You are representing this value as theta I, say theta I plus 1, that is say theta equal to n minus 1, say theta equal to n minus 1, that is at the midpoint. At the midpoint, minus say theta n minus 2 divided by delta x, say 2 delta x, right? Theta n minus 2 by 2 delta x. Now, what is happening? Although theta x, del x is nearer to 0 at theta n minus 1, upwinding scheme always replaces theta n by theta n minus 1. That is theta n minus 1. By 2 delta x. That means although del theta del x is nearer to 0, although del theta del x is nearer to 0 at theta n minus 1, upwinding scheme always calculates theta n minus 1 by this finite difference method. Right? So it is always calculus, although it is nearer to 0, but upwinding scheme always the diffusion term, del theta del x. Upwinding scheme always, it is not basically exactly calculating the diffusion term, but it is basically overestimating the diffusion term. So although del theta del x is equal to 0 at theta n minus 1, but this upwinding scheme, we are basically forcing to calculate del theta del x at a point where del theta del x is 0, at the midpoint of the grid for a very high Pickley number flow, which causes so basically it is, though it is 0, but we are calculating this. Though it is 0, we are calculating, though the value will be very less, but we are calculating this del theta del x term continuously, this upwinding scheme. That means it introduces an additional diffusion to the problem, which is called the false diffusion. This is the primary limitation of the upwinding scheme. Although del theta del x at the point where it is 0, closer to 0, is nearer to 0 at x equal to 0.5, but we are calculating del theta del x from the upwinding scheme. The upwinding scheme always calculates the diffusion term by taking an upstream value. That means if we calculate the diffusion term, it will add an extra diffusion to the numerical solution, which causes which overestimates the diffusion term at high Pickley number. That is called the false diffusion. So this is the problem of upwinding scheme of false diffusion. And to prevent the false diffusion, if you perform local refinement in the grid, or if you locally refine the grid, this problem of false diffusion can be minimized. So this is the limitation of upwinding scheme, and one may face false diffusion issue while applying upwinding scheme for a very, very high Pickley number problems. Although false diffusion is number of percentage of diffusion is very less, but still it sometimes overestimates the solution. Is that clear?
Yes, sir.
Sir, at x equals to 0.5, how the local refinement is done?
Okay. At x equal to 0.5. Okay. This is the 0.5. Right? This is 1. This is 0. So grid point, uniform grid point, uniform grid point, uniform grid point, delta x, delta x. Now, this is the local refinement. Clear?
Yes, sir.
Okay. Any other question? Have you understood this concept of false diffusion?
Yes, sir.
Okay. Any other question from any of you? Any other question from any of you? Shivnath, any question?
No, sir.
Okay. Okay. So this is all about today's class, and this is all about your upwinding scheme and this convective scheme for the numerical solution. Sometimes, please note that I have not written in this slide. Sometimes upwinding scheme is also called the convective scheme. Okay. So if someone asks what is the convective scheme you have used, so you have to say I have used first order upwinding, second order upwinding, or third order quick scheme. So upwinding scheme sometimes are called convective scheme also. Okay, this is the last slide actually I have presented you the first division. This is all about Apuni scheme. Next class, I will be starting another chapter, the last chapter of your syllabus, special topics. So this will be the last chapter. That will be last chapter of your syllabus. So there actually I will be discussing some primitive variable approach. I will be taking another 2 classes. Tuesday I will be starting the special topics chapter, and Tuesday maybe from in the evening I will announce soon, and followed by another class, the last class of your CFD course.